Hello, everyone. Today I'm going to bring to you another exercise of the two-sample t-test. But before I do that, I'm going to review a little bit what's the difference between each of these t-test types and when do we use t-test as opposed to other tests, statistical tests. Okay, here's the debrief. Matched pairs versus two-sample t. We should use matched pairs t-test if all units are measured twice. For instance, before versus after, or are matched in some way. For example, with weight. Why would we use matched pairs t-test for something that we are measuring before and after? Because those events are not independent. For instance, if you apply a topical cream on your skin and then test the effects of that cream a few hours later, you are the same person. Those events are not necessarily independent. Contrast that with using two-sample comparison of means. We use that when we have two independent groups and when each unit is measured only once, and there is no mention of units being matched or paired in any way. For instance, men versus women or treatment versus control. When is it okay to use T procedures? For one sample and matched pairs, for one sample T test and matched pairs T test, we use N as the population size. For a two-sample comparison of means, we use N equals the first population size plus the second population size. For the sample size, we use T procedures, and like using T procedures is heavily dependent on sample size. It's very recommended. For instance, if your population size is less than 15, and your data is normally distributed, that means there are no outliers or skew to the shape of the data. If your sample size is between 15 and 40, we can use T procedures except in the presence of outliers or strong skewness. If your sample size is greater than 40, it's okay to use the T procedures, even if the data is strongly skewed. But at the same time, there must be no outliers. So keep this in mind. So as a summary, which general statistical test should we use? Well, for quantitative data, for the confidence interval, we can use Z to estimate the range and the mean. And we use the Z-test when sigma, the standard deviation, is known. For a one-sample Z-test, we can use it to compare the mean to the claim, and we use it when sigma is known. For the confidence interval T-test, we can use for estimate and the range for the mean. We use this when sigma is not known, when the standard deviation is not known. The one sample t-test, we can use it to compare a mean to a claim, and we use this when we don't know the standard deviation. For a two-sample t-test, we use it to compare the means of two groups. They must be independent groups. For the paired sample t-test, we compare means of pairs, the difference between matched pairs. So in this case, our population size would be the number of pairs in our sample. Let's begin with a problem with our matched pairs t-test. Wait, no, not matched pairs t-test, sorry. Two-sample t-test. Two-sample t-test. So here's the problem statement. A manufacturer of a major hot dog brand is trying to make a hot dog that has the same great taste as its original hot dog, but with less fat. The company takes a random sample of 10 original hot dogs and 10 new hot dogs and measures the fat content in each. The data in grams are listed below. We would like to estimate the difference in mean fat content between the original hot dog population 1 and the new hot dog population 2, and we would like to determine the margin of error of this estimate with 98% confidence. Based upon the information provided above, is this an example of inferential or descriptive statistics? This is an example of inferential statistics, and I'll tell you why. Essentially, descriptive statistics states facts and proven outcomes from a population, whereas inferential statistics analyze samplings to make predictions about larger populations. In this case, we're trying to infer something about a greater population from a sample. So this is inferential statistics. Which of the following conditions is not verified? Part B. The samples are large enough to assume the populations of new hot dogs and original hot dogs are normally distributed. So this is not verified because let's take a look at the sample size. The sample size is only 10 hot dogs. That's not a very large sample size. So we cannot really assume normal distribution. Okay, part C, we want to calculate the point estimate in grams for the difference in population means. Well, they gave us a very helpful tool to do that. They say use salt. So I'll launch that software and we will see what it generates. Salt is a very helpful tool. And we can go to the descriptive statistics where we can see all the values we need in the summary table. In part C here, they asked us for the point estimate in grams for the difference in population mean. And over here, we see that the mean of the original hot dogs is 17.48. For the new hot dogs is 16.41. So what is the difference between the means? Well, the difference between the means is simply 17.48 minus 16.41, which is equal to 1.07. Now for the second part, the standard deviations, we can also retrieve that information from SALT. As we see here, the standard deviation for the original hot dogs is 1.588. For the new hot dogs is 1.1976. As we see over here, this is what we entered. Now we want to calculate the margin of error of the point estimate, which is the point estimate is basically the mean for the difference in the population means. We want to assume that the distributions of fat content in the original hot dogs and the new hot dogs are normally distributed. We can use a table or technology to find the t-value that we need to calculate the margin of error. Because to calculate the margin of error, in that formula, we need a t-value. We also need the standard deviation and the population size. So we will calculate that right now. So here's what we got. The formula for the confidence interval is equal to the mean plus or minus the t-value times the standard error. Over here, we have a pooled standard error because basically for a population size that is the same for both for both samples, we can simply use only n on the denominator, and then we can sum the squares of each standard deviation. This is the standard error for such a population. A population that involves two populations that have the same size, or two samples that have the same size. So the t-value, how we find that? Well, we know that the degrees of freedom is equal to 9, and we also know that it is at 98% confidence. So we can go to our t-table right now. Let's look at our t-table right here. So the degrees of freedom, we want to find 9 degrees of freedom, and afterwards we want to go and see where the 98-degree confidence interval is. Well, the 98-degree confidence level is right over here. So we simply find the 98-degree confidence interval and see where that intersects with 9 degrees of freedom, which is right over here. So we want the value 2.821 as our t-value. The margin of error that we need to find is this portion over here, the t times the t times the first standard deviation squared plus the second standard deviation squared. So the standard error So the standard error is thus equal to 2.821 times the square root of 1.5880 squared plus 1.1976 squared over 10. The population's the sample size, I mean, and this all is equal to a standard error. Wait, no, not a standard error, but margin of error of 1.77. As we can see here. Thank you all so much for watching this video. I hope this video has helped you guys, and I'll see you next time.